Welcome everyone. This is the second part of the TCD1304 linear CCD video series. And in this video, I'm going to show you how to program this microcontroller here in order to be able to drive this CCD and send its output data to your computer via USB. So this will be a bit longer video, and it will be focused on programming mostly, but since there are no good resources on programming a microcontroller for this specific CCD on the internet, I could not find any, let's say, exceptional resources. I thought that I should publish my stuff so people can probably easily learn it, because as you can see, or as you will see, it is relatively fast to set up the microcontroller in order to control this CCD. But in order to be able to do that, we have to deeply understand how this microcontroller works and how the CCD works. So how the different gates are clocked and how they work, how we read the pixels, and how we, for example, apply a certain integration time, and so on and so on. So this video will be about this sort of step-by-step procedure of setting up the microcontroller, this specific STM32F401 microcontroller for driving this TCD1304 CCD. So the circuit is actually not too difficult. We have a simple microcontroller and a bunch of wires which are connected to the basic circuit, which is actually from the handbook or manual of this CCD. So I just copied that circuit, and then I used KiCad, drew a very simple schematic and not so well designed PCB, because of course this is electronically could be improved, so we could have less noise, but it's enough to drive the CCD. So as you can see, the whole custom circuit is located on a PCB. So here's the CCD and some circuit which serves the CCD. And this is a good opportunity to introduce the sponsor of this video, PCBWay, who actually manufactured this nice PCB for me. So let's see what they can do for you. So once you have your PCB design ready, you should head to PCBWay.com and order your PCB from them. And this is really easy and straightforward process. You just go to PCB Instant Quote, select the desired option, standard or advanced PCB, upload your Gerber files, and finish by customizing your board. And speaking of customizing, I recommend you to check their advanced PCB option, because they recently added some nice solder mask colors. So even if you don't want to have some special board, but want to have some unique looking PCB, you should check this option out and select your favorite color. And let me tell you that you can even win with this unique looking board several valuable prizes, because you can participate in PCBWay's 4th PCB design contest, and by participating in this contest you can really have some really nice prizes. And if this would not be enough for you, then once you have ordered something from them, you should really share a detailed feedback which can lead you to participate in another event from PCBWay. And then by sharing your order feedback, you can also have some really nice prizes. So coming back to this circuit, now everything is just set up. I set up the timing and everything for the oscilloscope. So actually what we see in between these two peaks, these are the two like initial dummy pixels when we start the timer, which triggers the ADC, but there is no data to read by the ADC because the rest of the things are not there yet. So in between these two peaks, we are supposed to be seeing the CCD signal. And if you have noticed, when I was pointing at the CCD, there was already something jumping here. So if I put my finger in the middle, you can see that that's my finger. And if I put on one side, you can see that that's my finger on this side, and then of course I can do the opposite. And if I just take a piece of wire, put it over the CCD, then that's pretty much the peak coming from the two wire or the shadow of the two wires. So that's very, very good. So even thin stuff can be captured with this CCD. And of course that's obvious that we should be able to do that, because 1 pixel is like 8 micrometer wide, so we can detect very tiny shadows. But you can see I have a thinner wire and it works very nicely. And as you can see, unlike other demonstrations, there is no need for electrical tape. There is need for the knowledge of how to program this thing. So you can set up the integration time properly, and you don't need to cover the CCD, because if you use short enough integration time, of course you will not have the problem of the overexposure of the linear CCD. So as you can see, it works well, and it's a very high FPS, so you can see that how fast I can move my finger and it will do the stuff quite nicely. Of course the signal jumps a little bit, it's not optimal, but you can see the main things that you should see. So as you can see, the circuit works. And in fact, I will show you that the circuit can also forward this data to your computer, and then you can visualize it however you want. So now this will be a programming part. So let's head to my computer and see how to set up this CCD. So first of all, let's talk about how CCDs work in general, and then we will talk about the general principles of this specific CCD. But before that, let me mention these two gentlemen in the golden frame who earned a shared Nobel Prize for inventing the CCD. So you can see that this device is quite highly appreciated in the scientific community, so it could even earn a Nobel Prize. So in this video we are talking about quite a famous invention. So keep this in mind. So here is a very oversimplified explanation of how a CCD works, but of course I will explain what is visible on the picture. So we have a carefully crafted layers of different kind of silicon oxide and p-type doped silicon and so on. And what is happening with this silicon is that when it is subjected to light, then the incident light hits the surface of this CCD, and then it creates holes and electrons. And then out of these two, let's call them now particles, the negative charge, the electrons, is captured. And the capturing happens in potential wells which are created inside this CCD sensor. And what is happening is that this accumulated charge, which is proportional to the incident light, is just accumulated. And after the exposure is finished, we shift out the charge packages or packets, and then these charge packets are converted into some digital signal by an AD converter. And how it is done is that these charge packets can be moved with this positive bias. And how it is moved is that, for example, I just put this one single potential valve with a few charges, and then if the positive bias on this side becomes more positive than here, then the charge starts to being transferred into this part. So then this potential valve becomes empty, and this will store the charge of this previous potential valve. And then we increase the bias of this third gate, so it will be higher than the second gate's bias, and therefore the charge which we have here will migrate here. And then this is continued until the charge is being emptied and being transferred to the AD converter, which measures basically the voltage or current, depends on, and transforms it into a digital signal. And then everything starts over. And how this is moved out is basically we just apply some clock signal, so then the clock signal will control the sequence of the change of the bias here on the different gates. And then with this clock we will just move out, so there will be a certain frequency how this being moved out, and we will actually create this frequency, and we will take care of the rest of the things. So this was just a very oversimplified explanation on the CCD, but hopefully you understand how it works in a very, very simple level. So let's go to our specific TCD1304 CCD, and this is the circuit diagram of it. So in the middle we have the photodiode part and the dummy pixels, which are marked with D something. So on both sides of the S letter pixels we have D letter pixels, which are dummy pixels, and then from S1 to S3648 we have the useful or effective pixels. So then we have two integration clear gates, and they just, if I know it correctly, clear up the charge prior beginning of the integration. And then we have the shift gate, that is the SH, and that acts as a shutter. So you can turn it on and off, and when it is on, the incident light will be captured as a charge, and when it is off, the incident light has no effect on the charge collected inside the CCD. And then we have the analog shift registers, which basically collect these pixels and shift them out to the output of the CCD. So that's where the clock is needed to just push out everything with a certain sequence. And here we see the three signals that we need to feed to this circuit. So we have to take care of the integration clear gate, we have to take care of the shift gate, and then we have this phi m, which is the frequency fed to the CCD analog shift register, which will just sweep out the pixels. So this is from the datasheet again, and here we can already see some specific parameters which we will need to know for the programming part. So these two lines or rows in this table are very important. So f phi m and f data are frequencies. The first one for the master clock pulse frequency, and the second one is for the data rate. And what this tells us is that we will use the typical values, and this means that the master clock pulse frequency, so the f phi m, should be 2 megahertz. So now we already know that we have to feed at least one signal to the CCD, which has to be 2 megahertz. So here we just say that one signal will be 2 megahertz and 50% duty cycle PWM signal. And then we have the data rate. So this is the rate how the useful pixel values are shifted out, and here that is 0.5 megahertz or 500 kilohertz. So again, we know the next thing that we have to know about is that the data rate of our AD converter has to be 500 kilohertz, which means that the signal of the timer which triggers the AD converter has to be triggered with 500 kilohertz. So this will be our signal. And then basically that's all. On the bottom I just highlighted the two most important things, just to know. So then how to manage the rest of the signals, then that comes here. So this is a timing chart, and it's not a one-to-one timing chart. So this is just the sketch of it. But what happens is that if we start from the top, then we see the SH signal, which is the for the shift gate. And then you see that this is a simple pulse. Here it is shown as a 50% duty cycle signal, but in our case it won't be a 50% duty cycle signal. You will see it, what it will be and why. But what we know here is that one period of this pause is the integration time. So if you change the period to larger and larger numbers, you increase the integration time. And from this chart, we can also read that in fact the ICG starts the exposure, and then as long as it is high, the integration is going on, and we capture the data, or basically we capture the image with the CCD, and when it goes low again, then the data stream is basically finished. And then we can see that our SH signal should be, let's say, squeezed in between these two integration clear gate signals. And then we see that this is the 2 MHz signal, the phi m, and there's nothing really specific about this. We don't have to know anything. And then on the bottom we just see the OS, which is the output of the CCD. And as I said in the previous figure, we have some dummy elements, which is like 32 elements in the beginning. And after these 32 elements, we have these 3,648 elements, which are the useful pixels. And after that, we have another 14 dummy output. So we have to reject those pixels as well. But of course, for the sake of simplicity, we capture everything, and afterwards on the computer we do some data processing just to get rid of the useless values. So now let's take a closer look at the timing of SH and ICG, because this will be one of the hardest tasks in the whole programming, I would say. It took me some time to figure everything out, but I solved it and it works perfectly. So as you can see, there are some periods defined here, starting from T1 until T4. So we have to consider these numbers very carefully. So what happens here is that basically what you see is that first the ICG goes low here, and then there is a tiny delay between the ICG going low and SH going high, and that is the T2. And here the T2 is typically between 100 nanoseconds to 1 microsecond. And in my example, I will use 600 nanoseconds. So here you see that, first of all, we will have to generate 2 more signals from the output of the microcontroller, SH and ICG. They will be also PWM signals. And then after the ICG is going low, we have to start the SH within maximum 1 microseconds, and I will start it within 600 nanoseconds. And then SH should be kept high for T3 time, so it should be high for at least 1 microsecond. It doesn't really matter whatever you choose above 1 microsecond and below this length, or the length of the ICG being low. I picked 4 microseconds because actually this length is much higher. If you just look at the typical values, then we have for the ICG being low, T2 plus T3 plus T1, which is actually at least 6,500 nanoseconds, so 6.5 microseconds. So we keep the T3 high, or the SH high for T3, and that is at least 1 microseconds, but I will keep it for 4 microseconds. And then until it went low, the ICG should go high within T1 time period, which is typically 5,000 nanoseconds. I will have 6,000 in this example. And then there is a T4 timing as well, but as far as I'm concerned, if you just directly start all the timers at the same time for the on the microcontroller, nothing bad will happen. So the signal will be shifted out properly. And if you use the electronic shutter, then of course we have to make sure that we generate some carefully considered square wave between two ICG pulses. And the minimum integration time is 10 microseconds. And actually that is what I explained, that my T3 is 4 microseconds and my T1 is 6 microseconds. So 4 plus 6 is 10. So that's why I picked these numbers like that, because then my 10 microsecond minimum integration time comes out very nicely. And then the maximum can be anything, but I will keep it at the same level as the length between two ICG pulses, so basically the readout time. So then finally, just let's look at the circuit. So this is the circuit which I just put in KiCad and designed the PCB for. And as you can see, here we have a hex inverter, and then some capacitors, some resistors, and a PNP transistor, whose base is connected to the OS, the output of the CCD. And then, yeah, there is nothing extraordinary about this thing. It's not the most ideal circuit for driving this CCD, but it works. In fact, you can skip using hex inverter. You just have to pick the proper polarity when you write the code, and basically that's all. So then I would use an op-amp for this OS output, and I will do that in a later video where I will design a better circuit and PCB for this CCD, because it deserves it. So technically that's all. So now I will go to the STM32Cube IDE, and from scratch I will write the code and show you how to make it work. So let's start by creating a new project in the STM32Cube IDE. So I just start a new STM32 project. And then we select the microcontroller, and the microcontroller that we will use is the STM32F401 CC. And I already have it among my favorites, so I just click it. You can see the reference, CCUX, and then click next. Then here you have the location where you want to save it, and we give some good name to it. So it will be an STM32F401 and TCD1304 CCD, and let's call it demo. So nothing else has to be changed here, we just click finish. So once the software finished creating the project, you should see this display where you can see the pin layout for the microcontroller, and you can see the peripherals and other components of the microcontroller on the left side here. So far it's quite easy, and now we can start to actually work on the microcontroller and generate the code and so on. So first of all, we know that we want to have the data on our computer through USB, and then the USB needs a high-speed clock. So what we have to do first is that we go to System Core, and we have this RCC here, and we have this high-speed clock HSE, and we put it and select ceramic resonator here. So now this means that the microcontroller uses an external clock source. So this is done, and now we can configure the USB. So first of all, we go to the connectivity, close this, and we select USB OTG FS, and here we just enable the device only mode. Nothing else has to be changed, but we have to go to the middleware, and we select USB device, and we have to change the class for virtual COM port, so communication device class, and it's done. So now we have a USB. So this will mean that the microcontroller will be able to send and receive data through the USB. So now as this is done, and we have our external clock source. We have to configure the clock. So we go to the clock configuration, and then here the software suggests or recommends that you have to automatically run the clock solver. And you click no here. And why? Is because the default value for HCRK is 16 megahertz, which is too low for us. So we press no. So after pressing no, we simply select this field and replace the value with 84, which is the value that we want to have. And now it says that no solution found, blah, blah, blah. So we click OK. And we wait. And after some waiting, as you can see, everything is figured out, and we have the proper clock frequencies. So this is done, and now we can go back to the pinout and configuration, and we select the timers. And before doing anything, let me talk about the timers in very short time. So as you can see, this microcontroller has a bunch of timers, and we will use timer 2, 3, 4, and 5. Timer 2 and timer 5 are 32-bit timers, so they can count to very, very large number. And timer 3 and 4 are 16-bit timers, so they can only count up to 65,535. But that is also enough for this purpose. But we are very lucky that we have the 2 timers with 32-bit resolution, because we will actually make use of it. But how they work is, you can see it on the illustration. So we have this CNT register, and that counts up. So the value of the CNT is incremented by each clock pulse. And the clock pulse is provided by the CPU. And that is this 84 megahertz signal. So this 84 megahertz signal creates a pulse at every 11.9 nanoseconds. So we increment the value of the timer every 11.9 nanoseconds. So then there are 2 main registers which we use in a timer. One is the auto reload, or ARR register, and its value will determine how long you will count before resetting the counting or making the register to overflow. So for example, if you set this value to 3, then you count down 3 clock cycles, so roughly 36 nanoseconds, and then you start over. And we have another register, which is the capture compare, or CCR register, and that determines when you flip the signal of the output, basically, of the PWM signal generated by the timer, or this is how I interpret it. So first, always the CCR register is let's say triggered in a normal setup. So as you can see, you start counting, the PWM output is high, and when the value of the counter reaches the CCR, the output goes low, and it stays low until we reach the ARR register. And then everything starts over. So you can also see, actually from the middle section of this picture, is that the period between the CNT equals 0 and CCR value will make up the duty cycle of this PWM signal. And the interval between CNT equals 0 and ARR, the value of the auto reload register, will make up the period of the generated PWM signal. And basically this is all what you have to know about timers in this case for this demonstration. It will be enough to understand how the CCD is driven. So the CCD is driven by 3 PWM signals, and we have to know how we manipulate the PWM signals, their period and their duty cycle, with these timers, so we can drive the CCD properly. So now we can start with the simple timers, so the 16-bit timers, so timer 3 and timer 4. I would like to start with timer 3, and that will generate us the main clock, the 2 MHz clock. So here we have to select internal clock as the clock source, so this timer is fed by this 84 MHz signal, and then we simply select channel 1 and PWM generation CH1. So this will mean that, as you can see, a pin popped up here. This will mean that on the PA6 pin we will see this PWM signal, which is generated by the timer 3. So now we have to look at the auto reload register and the capture compare register, which here is the pulse. So we know that the main clock is 84 MHz, and we know that we want to generate a clock which is 2 MHz. So the relation between them is 42. So 2 MHz times 42 is 84. So what we have to do is that we enter 42 minus 1 here. Minus 1 is because in the background the software always adds up or adds 1 to this number. So in order to keep it at 42 we have to subtract 1, and you can write it in this format so it will not be forgotten that you actually did a subtraction of this one here. So now this will count 42 times 11.9 nanoseconds, and that will give us the 2 MHz signal. And also now we want to generate a 50% duty cycle clock. So that means that the CCR has to be the half of the ARR. So then this becomes 21 minus 1. And that's all. So now we can move to the timer 4. So the timer 4 will be used to generate a signal, not an output, but a signal for triggering the ADC conversion. And that is very simple. We need a 500 kilohertz signal. So what we do first is that we select the internal clock here again, and here let me select a different channel, the channel 4 for the signal, because other channels will be not suitable for us in the future. As you will see how we develop the code, you will see that it doesn't work. So now we just want to generate a PWM, but no output. So we have this PWM generation no output, we select that, and then we want to generate a 500 kilohertz signal. So 500 kilohertz is actually 1/4 of 2 megahertz. So we have to multiply the 42, which we used here previously, by 4. So that is 168, and we just subtract 1. And that's all. And here, the pulse, I say that since the triggering is only operating when the PWM signal has its rising edge, it doesn't matter really what the duty cycle is, but let me make it 25%, so 1/4 of this value, which is 42. And 42 is a nice number, so why not use it? And now basically this is all that we have to do here. So now comes the more complicated timers, timer 2 and timer 5. So these are the 32-bit timers, and we also know that we want to trigger the SH with the ICG signal. We first have to look into the data sheet, the reference manual of this microcontroller, because we want to see the internal triggers. And we will see that the timer 2 can trigger timer 5 via ITR0. So this means that the timer 2 becomes the timer for the ICG, and then timer 5 becomes the timer for SH. So let's go to timer 2, and we select the clock source, internal clock, and we simply go to channel 1. Here we can go back to channel 1 and PWM generation channel 1. So now we have to think a little bit how to set up the ARR and CCR registers. And what we know is, we know the readout time, so the time elapsing between two ICG pulses, and that is basically coming from the 500 kilohertz signal, which is the trigger for the ADC, and that gives us 2 microseconds period. And then we also know how many pixels we have, and with the dummy pixels together we have this 3600 something pixels. So then we know that basically we have this 3694 times 2 microseconds, so 7388 microseconds of total readout time. So let's round this up to 7500 microseconds, and if we calculate this as a frequency, or if we calculate this as a period, then we know that in order to make 7500 microseconds, we need to multiply the 11.9 nanoseconds with 630,000. So 630,000. And here you see that actually this would not fit into a 16-bit register, because that can take just 65,000 something. So then here it's very useful that we have a 32-bit register. So that's very nice. But actually we can use a 10 time prescaler, and then this becomes 63,000 instead of 630,000. So actually we could cheat a little bit, but I don't want to use the prescaler right now. So since we have the 32-bit timers, why not use it? And then we also know what kind of duty cycle we want, and that is coming from the timing diagram or from the datasheet. And based on the calculations and our own values, that is 0.13333%, and that means that if we calculate from the ARR, this value, the pulse or CCR, should be 840 and minus 1. So this is done, and what we have to know, if you remember, this will be a trigger. So we have to enable the MSM bit, and how we trigger is that whenever the CNT enabled is done, we also trigger the other timer. But with this, we are basically done with the timer 2. So we jump to timer 5, we select internal clock, and again I know that there will be some conflicts in the future because of the ADC. I go for channel 3, and then PWM generation CH3. Again, we are very happy about this 32-bit timer, but in fact we will not need it. But now I select a random integration time, which is, let's say, 20 microseconds. So 20 microseconds in this counter period is 1680 minus 1. And this comes with a certain duty cycle, and that is 336 minus 1. And one very interesting thing is that actually this number will be always the same, whatever value you choose for the counter period, but this is how the duty cycle will change. So the longer the counter period is, so the higher or larger number you enter here, the smaller the duty cycle will be. And once again, here we just set up the timers. We have to remember that this is actually a slave, so we have to activate the trigger mode, and the trigger source, as I said, based on the reference manual, it's ITR0. So we check that all the numbers are fine. We enable the MSM bit, and finally we don't do anything here. So opposing to the other, we had to select the enable here, but we just keep it as reset. And this is done. So once we are done here, we can actually press the save button, which will generate the code for the microcontroller. So now we wait a little bit, and then we go to the main.c file. So here we have the project explorer, and under the core and src we have the main.c. So right click and open, and we have this huge bunch of code. So now you can see that this part was, for example, automatically generated. And what we have to do here is that we have to start the timers, because here they are just initialized but not started. And how that happens is that you start typing HAL, TIM, and PWM and start, and you press Control, hold it down, and press space. And then here it says what you should, what you can do. So you can start the PWM by itself, or with DMA, or with an interrupt. But we start normally. We select the timer. So now that will be, let's say, number 2. And we know that the timer 2 uses the channel 1. So TIM, you can press Control space. And then if you scroll down enough, you should be able to find the channel 1. But of course you can type it, because as you can see it's a long list. Channel 1. So this is done. So now I'm cheating a little bit. I know that we have 3 more. So timer 2, we know that that is actually the ICG. And then we have timer 3. And timer 3 uses channel 1, so we don't pick it. And this is the phi m. And then we have timer 4, so we start it. And timer 4 uses the channel 4. So let's go there. And timer 4 was used, or is used, for the ADC trigger. And finally this will be, of course, timer 5. And timer 5 uses the channel 3, and of course this is the SH. So everything is done, and all we have to do is we just start and click run with this button, so it will create the files. And here, as you can see, you can select the debug configuration. So here you just have to make sure that it is pointing at the correct file. But in the debugger, here the debug probe should be OpenOCD, and then you should go to show generator options, and the reset mode should be software system reset. So you apply and click OK. So the building was finished, and no errors were showing up, so that's gorgeous. And of course I haven't connected my ST-Link, so I will do that and show you what we get. So I connected my ST-Link, uploaded the code, and I can see the signals on my oscilloscope. Here is one, for example, with a lot of ICG pulses and even more SH pulses. So you can see that the signals are generated. But if we zoom in, you can see that it is pretty much aligned, which means that there is no delay between the ICG and SH, but we need a few hundred nanoseconds of delay between the two signals. So ICG should change its polarity first, and then SH should do it as well. And I haven't mentioned it, but the polarity should be also fixed. It's fixed on this picture, of course, but on this picture it is according to the same polarity as it is shown in the datasheet. But if you use the hex inverter as it is suggested by the datasheet, actually you should invert the polarity of these two signals, because they will be inverted by the hex inverter. So keep this in mind. And how you can do that is you go back to the configuration, and you go to the corresponding timer, which will be timer 2 and timer 5, and you make sure that you generate the proper cycles. And there are just 2 timers and 2 different options, so you can have 4 different things, so you can figure it out quickly. if you don't have an oscilloscope, for example. So everything is fine, but we have to add the delay. And there is a cheating for that, and I show you how to do that. So we know that the timer 2, the ICG, should be shifted a little bit backwards. And how we do that is we have these two lines here, and then time, and then set counter. So this directly writes into the counter register. And we have the HTIM2 and 66. And this will give us exactly 600 nanosecond of delay. And now, as you can see on this picture, the delay is perfectly there. So we can drive this CCD now. I just have to make sure that the polarity is according to the hex inverter circuit. So I go back, and then I select timer 5. And with the hex inverter, timer 5 should be low, and timer 2 should be high. So I just press build again, so this will set up the timers properly, and also it will compile the code and send it to the microcontroller. So essentially we are done. We are done here. The CCD is driven, and I put a few wires on top of the CCD, and I can see there are 3 peaks, and you can see the 2 big peaks shown with the arrow. Those are the dummy pixels in the beginning and in the end, and you can see that they are coincide with the ICG pulses as well. That is the yellow signal there. So it works extremely well. So now the next task is that we need to work with the ADC and the DMA and the USB. So the ADC will capture the output of the CCD. The DMA, direct memory access, will take care of these numbers which are generated by the ADC without involving the CPU, and then the USB will help us to send the data to our computer. So first, let's start working with the ADC. So we go to the analog part. We only have one ADC, and I select channel 3, so in 3. And then we can immediately set up the trigger. We know that the timer 4 is triggering the ADC, so we select timer 4 capture compare 4 event. And this is why I haven't selected timer 4 channel 1 in the timers, because there is no capture compare event for it. So let's just select this, trigger detection on the rising edge. So this is how it is. This is fine. And what we should select here is this should be enabled, but we don't have the DMA yet, so we have to add it. So we go to System Core, DMA, we have the DMA2 tab, click Add, and then here you select ADC1, and basically this is all. You don't touch anything. It's half word data width, and the mode is normal in this case, because we will generate the continuous requests always, so no need to change it to circular. It works at least like this. Why change something which works? We go back to ADC, and now this can be enabled. And basically, it's done. The ADC and DMA part is pretty much done. So now our only part is to write some code which makes it possible to store the ADC values and send it to the USB port. So let's go to main.c. So I go up to user code begin, and let's define a buffer length. So I say that define CCD buffer, and let's make it 6000 pixels, just for sake of simplicity. And then we make a volatile unsigned integer, 16-bit, and let's call it CCD pixel buffer, and then of course we want to put the 6000 in this. This will be a buffer, so it will be an array. And then here is just CCD buffer. Done. So the individual pixels will be stored in this array. Now we have to go down. There is a user code begin 4 here, and whatever we write in between these two lines will not be removed when we regenerate the code with the software. So now here we have to use our own code, and in this place we have to use the function of the ADC, which is called when the ADC conversion is done, and that is the HAL ADC conversion completed callback function. So once we measured our pixels, we have the pixels in the DMA, and then we want to dump that bunch of pixels on our USB. So here we have to call this conversion completed callback function, or it is being called automatically, but when it is being called automatically, we have to call a function which is the CDC transmit FS, which will dump the content of the memory, the CCD pixel buffer variable array on the USB. So I just do a copy paste here because it is annoying to always type in. So this is the function which is the callback function of the conversion completion, and then this is the function which has two arguments. One is the CCD pixel buffer and the length of this buffer, 6000, and here this is an 8-bit integer. So in fact, when you check the output data on the ADC check the output data of the ADC on the USB, you will see a bunch of random characters because you get the binary data. And it's not enough that it is binary, but it is split into two parts, two 8-bit numbers. So on the receiving side, you actually have to capture this data carefully and then combine two adjacent numbers, pairs. So number 1 with number 2, and then number 3 with number 4, number 5 with number 6, and so on from the array. You have to combine these two 8-bit numbers into a 16-bit number, which will be your finally your 16-bit integer, and that has to be converted into a normal decimal number or something that is human readable. So this is done, and now we have to start the DMA. So we go back to the main function here. And what we do here is that we have to call the DMA. And again, I just do some copy paste because it's just annoying to type it in over and over. And you have to be careful not to put it in this line because this will be removed by the automatic code generation, but you can put it here. So this starts the DMA in every iteration, and then DMA will do something if there is something to do. So it uses the handle for the ADC. And then we have our pixel buffer, the array, and the length of the array, 6000. And I just rearranged something here, but what is very important is the DMA always has to be initialized first, and then the ADC. So whenever you go back to this part here, you modify something and you press save, then this part of the code is automatically regenerated. And if you change something, it might happen that the order of these things change, and it changes in the wrong way, and the ADC is being initialized first, and then the DMA, and then you will not see anything on your in your buffer because it's not initialized properly. So always check this, double check this, that first the DMA is initialized and then the ADC. So now I upload this code, and then I switch the ST-Link to USB connection, and we will see what happens on the serial terminal. So I use this cool term. I recommend you to use it because it's a nice terminal. So if we press connect, then we should see a bunch of crazy pixels. and these are the crazy pixels. And now I just cover the CCD. You see that we get quite consistent data. And now I reveal the CCD and we get this because it's a huge bunch of noise. And I cover the two sides, we get this. So this is a pure binary number. So now I want to show you my software, which is a very, very simple software, but actually we can see what happens on the CCD. So let me start that software. So this is the plotter. There is a chart here, start and stop button. I can follow the time and the incoming bytes, and I can connect to the serial port. So I connect to the serial port, and then I start. And you see the dummy pixels jumping because I haven't done any careful timing here. So please notice that the image is crap because I haven't yet developed this software properly. But I put my finger on the middle of the CCD, and that's you see the signal. If I stop it in the right moment, this here is my is the shadow of my finger, and then this is one side of the CCD which is revealed more. Now I remove my finger, restart this thing, and it's empty. Now I put a piece of wire over this CCD and shift the wire, so the shadow of the wire should show up. There you go, the triangle, you see it, and I shift it, and you can see that it goes to the other side. So now we are at the other side, closer to the dummy pixels, and then I come back to the right side, and you see it. So it works, and this was all. It was quite simple. So now the next steps will be to develop this software more carefully. So for example, I can set up the exposure time or integration time, to be more precise with the definitions. So the integration time can be set up in this software, and I can send it to the microcontroller, and then the microcontroller will actually use that. So that will be one step. I will make this software better, so it will capture the signal properly, there will be no jumping, and so on and so on. We can save the data file on a TXT file or in a TXT file if we want. We can also change the FPS, for example, because now it's just dumping the data as fast as possible. So basically 1 second divided by 7.5 microseconds. So this is like the theoretical FPS right now for this CCD, quite fast. So the FPS will be changed. We can average the signal, and a lot of signal processing thing will be here. Why? Because now I will use this CCD and I will build my own spectroscope. I already have the prism, I already have lenses, I already have an optical grating. I have basically everything. I bought 3 different lasers to calibrate everything. So after this video, I will make a proper software, and after that I will make the first cool hardware which is based on this CCD, and that will be basically a visible light spectroscope, and you will see how cool it is. So now basically this is all, and as you can see, if you know what you are doing, you can write the code for this CCD to drive it and read it and display it within like half an hour, 1 hour, so it's not a big deal. But honestly speaking, I spent several months to learn everything, especially the STM32Cube IDE, because I haven't used it in the beginning, so I have to learn it. But now I finally can present it to you, and hopefully this will be a very useful guide for this specific CCD. So don't forget to visit my website, curiousscientist.tech. It is full of information. I put a very detailed tutorial, so check the description and you will see how to write this code. If you don't want to follow the video, you can follow the pictures and so on my website. And you can also find links where you can buy the microcontroller and also the CCD, so you can easily make your own CCD driving circuit. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.